Good day all, and you're welcome to class study session 7 unit 2 non-parametric test. Objectives of this study unit. The objective of the study unit are 1. To understand the concept of non-parametric test and how they differ from parametric test. Recognize situations where non-parametric methods are more appropriate, especially when assumptions of parametric test, that is the normality and equal variance, are violated. Learn the procedure and application of the sign test for testing hypotheses about the median of a population of paired differences. Understand and apply the Wilcoxon rank sum test as a non-parametric alternative to the two-sample t-test. Interpret the results of the sign test and Wilcoxon rank sum test in real-life context. Study the advantages and limitations of non-parametric methods compared to parametric test, and choose between parametric and non-parametric approach depending on the nature of the data and action. Learning outcome for study session 7 unit 2. By the end of this unit, students should be able to 1. Define non-parametric test and explain when they are preferred over parametric test. Identify situations where data do not satisfy assumption of normality. Perform the sign test to test hypotheses about population median or paired difference. Apply Wilcoxon rank sum test, which is also known as Mann-Whitney U test, as an alternative to independent two-sample t-test. Apply the Wilcoxon rank sum test as an alternative to independent two-sample t-test, and use critical values or p-values to make decision in non-parametric hypothesis testing. Develop decision-making skill for selecting the most appropriate statistical techniques for given data. Introduction. In many practical situations, the assumption required for parametric tests, such as the normality, distribution of the data, or equality of variance, are not satisfied. For example, data may be in form of ranks, categories, small samples where normality cannot be assumed. In such cases, non-parametric tests provide a powerful alternative. Non-parametric tests are also known as distribution-free tests. It does not require your data to follow a particular distribution because they do not rely on specific population distribution assumption. Instead, they are based on other signs or rank of data, making them especially useful for analyzing ordinal data or data with outliers. Outliers are data with extreme values in a data. They are widely used in business, education, medicine, psychology, and social sciences, especially when data are ordinal or when data are skewed or small sizes or samples are small in sizes. Tests like t-test and ANOVA, like the one we discussed in experimental design in study session 7 unit 1 that deals with analysis of variance, like the CRD and RCBD, they are like ANOVA. They assume normality, equal variances, and numerical data. When these assumptions are not met, we use non-parametric test, also called distribution-free test. Non-parametric methods are statistical methods that does not depend on a stringent assumption of population measure. They are used when do we use non-parametric tests? When we have uncommon mean of the distribution. They are also based on other signs or ranks instead of actual data values. Non-parametric test deals with situations where the population distribution are non-normal. That is, they do not follow a particular distribution, or they don't have any assumption. They do not follow any distribution assumption. So non-parametric test deals with situations where the population distribution are non-normal or unknown, when we don't know the distribution of the population, or when little is known about the distribution of the population under study, or when the distribution do not meet the requirement test, especially when our sample size is small, that is when our sample size is less than 30. It employs the median of the population and the method of hypothesis testing in conducting its test. Some non-parametric tests include sign test, which we'll discuss later. We have the Wilcoxon sign rank test, Mann-Whitney U test, Run's test, etc. What are the advantages of non-parametric tests? 1. Can be used with non-parametric tests can be used with ordinal or ranked data. 2. It does not require normality. It is robust to outliers and is suitable for small samples. What are the disadvantages of non-parametric tests? 1. They are less powerful than parametric tests. Non-parametric assumptions are valid and they provide less detailed information compared to parametric tests. Then the first one is the sign test. The sign test is one of the non-parametric tests. The sign test may be used to compare to population when samples are dependent, like the one we did for ANOVA for complete randomized design. But here, the sign test may be used to compare to population when samples are dependent. The other time we said when the samples are independent. It is very simple to use, but it is not a sensitive test. Sometimes it will fail to reject a false null hypothesis when another test will successfully in detection of the false of the null hypothesis. This is because sign tests throw away a good deal of information about the data. It also ignores the magnitude of the data value and only use the information about whether the data value is above the value of the median or. Now, the sign test is used to study the median of a population when the samples are dependent. We usually assume that the data is continuous. Purpose. Test hypothesis about the median of a population can also be used for paired sample, that is before-after studies. We set our hypothesis, set our null hypothesis should be H0, median equals to M0, no difference, and our H1, which is median is not equals to M0. For two-tailed test, it can either be greater than or less than, where our M0 is our one-tailed. Procedure. Test statistics. Number of data value in the sample above the median value given the null hypothesis. Then we have the significance level. We may be given to choose an appropriate significance level, or the examiner may give us the alpha level, which is our significance level. Critical region. When QX has a binomial distribution with n sample size and probability, which is our p equals to 0.5, we use table of binomial probability to find the critical region. Let me repeat myself again. Critical region. When true x has a binomial distribution with n sample size and our p is 0.5, we use table of binomial probability to find the critical region. If alpha is the desired level of significance, we choose critical value so that the probability that x falls in the critical region is close to as possible. We check whether the observed value x is the critical region or not. If it falls into the critical region, we reject it. That is our decision. We check whether the observed value x is in the critical region or not. If the observed value x falls into the critical region, we reject it. Otherwise, we do not reject or we accept our H0. So the procedures, the methods, how we estimate or calculate using sign tests. For number 1, for each observation, the first thing we do is we determine whether it is above, plus, or below negative, the hypothesized median. We ignore observation that is equals to the median. We count the number of positive and the number of negative. Test statistics, smaller of the two counts. Maybe it's the positive that is small or the negative that is small. Then we use our binomial distribution for small n or normal approximation for large n. That is from our table. So an example. A sample of 10 people report the number of hours they exercise weekly, which are 6, 4, 6, 2, 5, 4, 7, 3, 5, and 6. Test whether the median equals to 4 at our alpha level. Here our alpha level is given to be 0.05. Compare each observation with 4, plus 4 above and minus 4 below. From here, the first one is 6. 6 minus 4, it will give us plus 2, which is positive. The second one is 4 minus 4, that one will give us 0. The third one is 6 minus 4, that will also give us plus 2, but since it is a sign test, we are considering the sign. 2 and 4, 2 minus 4, that will give us a negative 2, so it's minus. 5 minus 4, that will give us a positive 1. Then 4 minus 4, that will give us 0. 7 minus 4, that will give us positive 3. Then we consider the sign. Please take note, we are considering the sign. 3 minus 4, that will give us negative 1. So we take the minus. 5 minus 4, that will give us positive 1. It's positive, we consider the sign. Then 6 minus 4, that will give us positive 2. So that one too will be plus. So the signs are plus, the first one, 0, plus, minus, plus, 0, plus, minus, plus, plus. Then we discard zeros. Then we count the total number of positive. From here we have 6 positive and 2 negative. Then our test statistics, which is smaller of the count of the two counts for small samples. So test statistics, the one out of the either positive or negative, we choose the one that is small, which is our negative, because it is 2. Then under H0, our probability is 0.5 and our n is 8. Then we use a binomial table at n equals to 8, and our p, which is our probability, is 0.5. When we check our table, probability of x less than or equals to 2 will give us 0.144. Then decision. Since our p is greater than 0.6, our p is 2, since it is greater than 0.05 from our table, then we fail to reject H0. Here, our p is 0.144. Since it is greater than 0.05, our p-value, which we get from our binomial table, that is, use binomial table at n is 8, p is equal to 0.5, p of x is less than or equal to 0.144, is greater than 0.05, then we fail to reject our H0, and we conclude that there is no evidence that the median differs from 4. Then the second, another type of non-parametric test is the Wilcoxon sign rank test. The Wilcoxon sign rank test uses more information than the sign test. It is used in investigating a single population median and to compare two populations using a pair of experiments. Purpose: we test whether the median of a single sample differ from an hypothesized value, or whether the median difference in paired or matched samples. We set our hypothesis that our H0, that is the two populations have the same distribution, and our H1, that is the two populations differs in location, which is the median. Procedure: let m be the value of the median that appear in the null hypothesis. Calculate x minus m for each data value x. We then rank the values and place a minus sign in front of each rank corresponding to a negative difference. Let W plus be the sum of our positive rank and W minus be the absolute value of the sum of negative rank. Then to test H0, given our median is equal to m versus H1, given our median is greater than m. We use W as test statistics. Then we find the critical value for a one-tailed test with desired significance level in the table of critical value for Wilcoxon sign rank test. It's also in our statistical table. So to test, this is for two-tailed. H0 given MD M versus H1 given MD is less than M. Also used for the third test. We use test statistics if we reject the hypothesis. Then we also have the procedure on how to calculate that. We have our median difference is 0, no charge. Median difference is not equal to 0. That is for two tail. It is either it is less than or it is greater than. Then we compute the differences. That is before and after. Also remember that we discard our 0 differences. We rank the absolute value. Smallest is 1. We assign plus or minus of the difference to each rank. Then we calculate the sum of positive ranks and the sum of negative ranks. Then we test statistics. Our test statistics will be W, that is the Wilson ranks. The Wilson rank sum test minimum will now be T plus, T minus negative. Then we compare our W with the critical value from Wilson table, or we can also use normal approximation if our n is greater than 25. But in a situation where our n is less than 25, we use critical value from the Wilson table. Then example, a dietitian measures the weight in kilogram of 6 patients before and after a diet. This is the table. 6, this is the number of patients. Then we have before is 85, after is 80. The difference between before and after, that will be 80. 5 minus 80, that will give us 5. We take the rank of 5, it is still 5. Then we rank 5, then we do our sign rank. Since it is 5, that will be, we add sign to our rank, that will be positive. We do for 90, which is 2, the second person. 90 minus 88, that will give us 2. Our absolute value 2 will be 2. Our rank is 2, and we add sign. Since it is positive, we have sign. Then here now, 78 minus 79, it will give us negative 1. If we take the absolute value of negative 1, it will give us 1. If we also rank this, it will also give us 1. Then we signed the rank. Here the rank is 1. Then if we sign the rank here, it will give us minus 1. We do for others. Then we do our sum of positive rank is 5 plus 2 plus 5 plus 1 plus 2. That will give us 15. Then negative rank is just 1. Then our test statistics, which is minimum of 15 and 1. Which one is the smallest out of 15 and 1, which is our 1? For small sample, when our n is less than or equals to 5, we use Wilson sign rank critical value table. But when our n is greater than 25, we use the number. So our n is the number of non-zero differences. Our level of significance, which is our alpha, is e.g. like 0.05, 0.01, 0.99, like that. So for one tail or two tail test, if our W Wilson sign rank test is less than or equals to critical value, which we get from our table, we reject H naught. From the Wilson sign rank table, for n is 6, two tails at alpha 0.05 and critical value equals to 0. Then we check our critical value from the table. For our n, when our sample size is 6 and we are considering two tails at alpha equals to 0.05, from our table, from our Wilson sign rank critical value table, our critical value is 0. Then we take our decision rule. Our decision rule says we should reject H naught only if W is equal to 0. Then if you remember, our test statistics here is 1 because we are considering the minimum of 15 and 1, so it's 1. Here the decision rule says, let me repeat myself again, reject H naught only if W equals to 0. That is, all difference goes in the same direction, otherwise we fail to reject. So from here, since our 1, which is our test statistics W, is greater than 0, then we fail to reject H naught, or we do not reject H naught. And we conclude that there is no significant evidence of weight Reduction.